right, so this is to continue from, excuse me, from part one that I gave yesterday. And just to very quickly recap what was talked about in part one. Excuse me, I'm losing my voice. So the main thing that I really talked about was the basics of Weyl Kondo semimetal, in which the correlation effect in the form of a Kondo effect produces low energy excitations, which because of the low energy scale, it has features associated with states in the vicinity of the Fermi energy, features that include, in this particular case, the development of wire nodes that are pinned to the vicinity of the Fermi energy, and and also with small velocity. And that statements have a number of observable consequences, which I talked about. And also, this encodes the cooperation between strong correlation and symmetry, including crystalline lattice symmetry, and one can take advantage of that as a way of searching for new materials in this overall category, which I also talked about. So to get to these main points, I made a point about a few particular aspects of the electron correlation effect. One, if you treat Coulomb interactions perturbatively to infinite orders of perturbation theory, the quasi-particles are resilient. And so you're going to see a sharp peak in the sense that the width of this peak is small compared to the center of the energy measured with respect to the Fermi energy. And the area measures the quasi-particle weight. So perturbatively, Z is less than 1. And on the other hand, we are interested in the extreme limit of interactions, and even for a Fermi liquid, we're interested in the extreme form of Fermi liquid. And so that turns out to be useful to consider interactions as modifying the form of the building blocks from the bare electrons to something like localized moments, which are coupled to other degrees of freedom. And so that leads to the consideration of a particular type of systems, which is in this overall category of bad metals. And these are Kondo lattice models describing heavy fermions. And through the Kondo effect leads to these quasi-particles, which have non-zero weight, but they are very fragile in the sense that the quasi-particle weight could be as small as 3 orders of magnitude smaller compared to unity. And so what this set up, and that small quasi-particle weight is very much part of a story of setting up this strongly correlated form of gapless topological states with the topological features that are associated with excitations pinned near the Fermi energy. Now, what this also sets up is the possibility of going from 10 to minus 3 to 0 for the quasi-particle weight if we can introduce some competing interactions. So that allows us to go beyond the dictation that if I treat the Coulomb interactions perturbatively, I can never get out of the region of validity or domain of attraction of the Fermi liquid fixed point. And so that's really the stage that was set for the purpose of for this talk. And in this talk, I want to show that there's a route towards the breakdown of the quasi-particles completely. And in fact, we've reached a stage of considering this kind of physics such that we can use the resulting strange metallicity to sort of make use of that as a product for realizing various aspects of interesting physics and beyond in some sense, including, for example, quantum entanglement, amplified entanglement, which I will very briefly mention, but also for correlated gapless topological state that goes beyond the quasi-particle description. So that's the purpose. So I want to sort of go slow, just realizing primarily one main point, but setting the stage up for that. So where I'm headed is really about Weyl Kondo semimetal with quantum critical phases or quantum critical points in such a way that there's something like Weyl nodal states, but the nodal states are not quasi-particles. And at least in one case, we can even make a statement that's fractionalized in some particular way. So to do that, I want to describe, sort of going back to the analog of the extreme form of Fermi liquid, how we can break up the quasi-particles without worrying too much about topology, and use that as a stepping stone for achieving this goal. I will not have the time to really describe a new frontier, which was outlined in an extremely clear way by Ming Yi yesterday. I would give a little bit of pointer from a theoretical perspective. These are new platforms that could consider both the Fermi liquid form of Weyl Kondo semimetal and the form of Weyl semimetals that and other topological semimetals without quasi-particles, and it could, in principle, operate at higher temperatures compared to the kind of heavy fermion systems, for example, that we consider, which operates at a few Kelvin scale. So maybe that's also a prospect that's interesting and maybe even having some functionality associated with it. So this is really my main point of this second lecture. So let me get started. Back to the correlation physics. How do we destroy the quasi-particles and realize strange metallicity? And I already gave a prelude yesterday that if you stare at a color plot like this for the phase diagram, and in this particular case, they have fermion metals, but they're not alone. There's a whole list of materials platforms in which, if you choose to use similar color schemes, this plot was made by somebody who worked in Germany, but was from the Netherlands. So obviously he chose the color, his favorite color. This is probably made by a different national, so green somehow is a favorite color. But each of these color scheme represents the exponent being 1 in the temperature dependence of electrical resistivity. And that's a hallmark of the fact that the exponent is different from 2, either here, the blue ones, or the black and other colors representing gamma equals to 2. That signifies a potential, at least a candidate system for the breakdown of quasi-particles. But other quasi-particles really lost. So I think it's fair. Let me just, before I delve into a bit more of the details of the correlation physics, I think there is an emerging caricature of strange metallicity in part, and I would say even in a significant part, coming from studies in these quantum critical heavy fermion systems. Namely, in addition to unusual temperature dependence of electrical resistivity, there are a slew of other things like enhanced physical entropy, dynamical scaling, Fermi surface reconstruction, and loss of quasi-particles. And I'll run through these a little bit. So let's start from this picture, which was a little bit of a desperate way at the beginning of trying to understand some experiment. So the phase transition from antiferromagnet to paramagnet, that's very familiar form. Quantum phase transition of a similar kind is also relatively familiar form. But it turned out that in this class of materials, as I was showing in those colored plot of phase diagrams, there's some unusual dynamics, and we had the physical picture, but also some calculational schemes to show that you can have a type of quantum critical point that not only has the criticality associated with fluctuations of the magnetic order parameter, but also something that doesn't involve explicit breaking of symmetry, global symmetry, such as the Kondo effect in this case, which I said yesterday, that if you form Kondo singlet in the ground state, you end up with the heavy fermion state with large mass seen in specific heat, etc. And if there's a scale that's associated with that, if this scale collapses, we call Kondo destruction, then this ground state is broken apart. And so just like suppression of antiferromagnetic order, you have from the other side, you have a suppression of this Kondo singlet formation. And that kind of quantum critical point goes beyond the Landau description in the sense that fluctuations of the order parameter is not the only critical degrees of freedom. So it turns out that the criticality associated with the amplitude of this Kondo singlet, which again goes beyond the Landau because it doesn't involve global symmetry breaking, spontaneous breaking of global symmetry, leads to a number of observable consequences. The first of this is this omega over t scaling in the dynamics, and with unusual exponents. At the beginning, we were, Jane-Xin Zhu and some of us did quite extensive calculations, and the reason was that we really wanted to know not only this omega over t scaling in the dynamics, in this case, dynamical spin susceptibility, but also whether this exponent is fractional, because that was the two pieces of puzzle that was hinted, that was given by the initial experiment of Gabe Apley, Megan Aronson, and others. And after extensive numerical calculation, we were able to get the exponent, which is fractional and reasonably compares well with experiments. So that was a large encouragement. There's some physics associated with this. Omega over t scaling means that the only energy scale at the quantum critical point at a finite temperature is kBt. And so that means that dimensional analysis works, and that's the signature of an unusual fixed point. And so in many ways, we are looking for the fixed point. And in fact, if I had delved into the details of the calculations, I would have shown you that this critical point corresponds to a new fixed point that's entirely different from the Fermi liquid fixed point. And that distinctly fixed point, it's an interacting fixed point. That's why the only scale in the problem follows from dimensional analysis. So kBt is the only scale in the problem. What was still further more non-trivial was to determine this exponent, and we were able to determine that. So that with that encouragement, we followed logical consequences of this Kondo's scale collapse to zero. In other words, as I said yesterday, if you have a Kondo singlet in the ground state, you have a Fermi surface that's large. But if the Kondo singlet is destroyed, the Fermi surface becomes small. So across the second order phase transition, there's a jump of a Fermi surface, which was considered to be a highly unusual prediction at the time. But experiments since that time, including the Fermi surface evolution as a function of a control, non-thermal control parameter, as well as the direct measurement of the Fermi surface volume by quantum oscillations, show that, in fact, across the quantum critical point, there's a jump of the Fermi surface. At least the data, I think quantum oscillation measurement provides direct evidence for that. Fermi's, the Hall measurement provides consistency check for this picture. Now, then you say, oh, wait a second, how could that happen? if you have a second-order phase transition, nothing should jump. And so it turns out that what happens is that the quasi-particle weight for both large and small Fermi surface must go to 0 at the quantum critical point, and therefore quasi-particles would be completely destroyed. So at some stage, we worked with experimentalists on the Wiedemann-Franz ratio measurement, thermal conductivity to the electrical conductivity ratio that provides 10% evidence for 10% violation of that. So it was an indication that quasi-particles are lost, but 10% evidence was not considered to be strong enough evidence, at least by some in the community. So this is a short noise measurement very recently done by Doug Nathanson here with the MBE films from the Vienna group of Silke Paschen. And the experiment shows that instead of getting to something like, this is the Fano ratio, which is the noise divided by the average current, normalized appropriately, instead of square root 3/4, which would be strongly correlated diffusive metal, a prediction which was first time made by Yiming, who's Yiming Wang, student here, who's in the audience. And instead of being 1/3, which would be the weakly correlated Fermi gas-like system in the diffusive regime, this is substantially smaller. And so one can rule out that Fermi liquid parameters are responsible, and with various experimental checks, this the only so far the only explanation that could be consistent with data is a loss of quasi-particles. So it's a very hard thing to really test that quasi-particles have been destroyed, but this is the most direct evidence that exists so far. And so I just want to quickly recap. In an unusual form, here all the quasi-particles on the Fermi surface are lost. And that's very important because if it's only some selected portion of the Fermi surface where quasi-particles are lost, then it's very hard to use these low energy, such state to engineer the form of the single particle spectral function, for example, when it comes to engineering topological semimetals like Weyl semimetals without quasi-particles, because you may just run into the portion of the phase space, K-space near the Fermi surface in which quasi-particles are still intact. But here, the evidence, all these points to the description that all the quasi-particles are lost on the Fermi surface in a quantum critical regime. And so there's a few consequences associated with that. One of them was that it's a magnetic quantum phase transition. So naively, or following the Landau paradigm, only the magnetic fluctuations should be critical and maybe even rise to the level of omega over t scaling, but other sectors should not pick up singularity at all. And we had some theoretical reasons to think that when the Kondo effect is involved, after all, Kondo effect historically was first discovered not by magnetic measurements, but by charge transport measurement, that the charge sector is also critical. And experimentally, this was based, the evidence, the most direct evidence came from the measurement of terahertz optical conductivity, again at Rice, by John Kono's group, once again using the Vienna MBE film produced by Silke Paschen and her collaborators, which showed that the kind of omega over t scaling that I started with in spin dynamics, in fact, is picked up in the charge sector as well. And it turns out that statement has important implication for superconductivity, which happens in the charge sector, which I will not talk about it. But it led us to think that, well, if the charge sector are dragged into a singular form of response, being part of the agent of criticality in a setting where the magnetic degree freedom would have been the most natural agent that senses quantum criticality. What is behind it? And given that Kondo singlet is up, down, minus, down, up singlet states are maximally entangled state, entanglement seems to be a very natural agent for coupling the charge into the critical sector when spins should be there. So that actually motivated us to think about entanglement aspect. And I'm not going to go into detail of it, just report on one particular measure, which is like using the operators that you picked up of the system when you do something like a neutron scattering or other scattering experiments, using these operators to do the partition of the system for you, as opposed to be artificially partitioning the system to calculate something like entanglement entropy. And using that leads to this one of the quantum witness called quantum Fisher information. And we were able to do the calculation to show that the quantum critical point is where it's amplified. This is the quantum Fisher information normalized as a function of control parameter. And the same thing is seen when you stay at the critical coupling as a function of temperature, it increases. So it gives the multipartite entanglement, and combining with some other things allows us to say that it's a highly entangled state. And I'm not going to do just to this subject. Pontus Weyl is giving a talk this afternoon later in the session, and I think he'll talk about such things in much detail. And I should also mention there's an experiment coming out of Vienna, which with results which are qualitatively consistent with this. And so the final thing which I want to set it up was also part of a motivation to seek these topological semi-metal states without quasi-particles, was a phase diagram like this, which I'm not going to explain. I already mentioned yesterday as a part of motivation for this general line of thinking, but except to say that if I use the size of Fermi surface here, large and small, in addition, on top of the spontaneous breaking of the spin symmetry, anti-ferromagnetism versus not ferromagnetism, then the phase diagram is highly enriched. Just because the distinction factors, there are more variables that distinguish between these different phases beyond the Landau characterization in terms of order parameter. Now, if we are going to consider the possible topological states in setting in which these strange metallicity is happening, it also opens up in a way two-way street of using correlation to generate new type of topological states, but also the other way around, using topology to enrich the correlation phase diagram. So that's very much part of the motivation. Yes, please. Yeah, so maybe just hold on for like 10 minutes and I'll give one example. Sometimes we don't know the answer. We only know that quasi-particles are lost. Other times we actually know, we have the evidence for some other fractionalized excitations, for example, that take place. So quasi-particle becomes a composite object. They can be very sharp. So if you generalize, so I'm using the term quasi-particles are lost in the sense of Landau Fermi liquid-like quasi-particles are lost. There could be other sharp quasi-particles that could emerge. Good. So I'm ready to get to the main part of this talk, which is the Weyl Kondo semimetal in the regime where the quasi-particles can be destroyed. So again, this is the motivation, more even general motivation that I mentioned yesterday, that we want in a way to ask the question that the analog of the insulating setting questions where we can have fractional quantum Hall that's distinct from integer quantum Hall can there be topological states in the interacting settings that are not adiabatically connected to their non-interacting counterpart, but in these gapless settings. So in order to do that, it turns out that there's a methodological setup one has to do. And I'll take 2 slides for that. Namely, if we want to define the band topology, we use topological indices like Chern number. If we want to define band topology for Weyl semimetal, we can use Berry curvature, Berry flux that's quantized for an area in the K-space that surrounds the nodal point. Now, those are concepts based on block states of non-interacting electrons. If I want to consider such effect in fully interacting setting, the block states are no longer the appropriate states to deal with. And so it turns out that one can use a replacement. And the replacement is that instead of the eigenstates, the eigenvectors of the non-interacting Hamiltonian, which are the block states, we can use the eigenstates here called a V of some Hermitian form of the Green's function, and where little g are the eigenvalues. Except that if I solve a non-interacting eigenvalue, define eigenvalue problem, non-interacting Hamiltonia, I would end up block state that has a k index, some other band index, other quantum numbers, so internal quantum numbers. Here, you also have to use omega as an index. And omega, just because it's an interacting problem. Green's function is a matrix that defined both in the spatial dependence and imaginary time dependence and other internal space. So the statement is that just like block functions form a representation of the lattice symmetry, the eigenvectors, the Green's function eigenvectors form a representation of the lattice symmetry group. And because of that, the symmetry constrains the generalization of the notion of degeneracies or lack thereof. It turns out to be on spectral functions, but if the spectral functions has some peaks, even though it's not sharp peak, if it's still dispersing, then symmetry can constrain these dispersive modes, regardless of whether they are describing quasi-particles or not. So that turns out to be essential for what I'm going to describe. So here's one example. If I know how to, if I can consider the Kondo lattice Hamiltonian, which I've written down yesterday, which describe a lattice of spins, this cyan color arrow representing it, and a lattice of conduction electrons, that's the Kondo lattice Hamiltonian. Now, I could also consider generalization of that. I still have a lattice of spin 1/2 moments, but now I have 2 degenerate species of conduction electrons. And I need the right symmetry for these 2 species of fermions to be degenerate and also have the identical coupling with the local moments, the same degenerate Kondo coupling. If that were realized, this is called 2-channel Kondo lattice. As a part of correlation physics, especially for impurity models, this was understood by some giants in the field like Philippe Nozier and others, that the local moment wants to form singlet with this species of conduction electrons in the way that I described yesterday. But the local moments has equal tendency of forming singlet with the spins of the other bands of conduction electrons. And so that's a frustrated situation. You cannot produce singlets simultaneously, and the compromise that's reached is a state that's not a Fermi liquid. And so this is shown, for example, this is based on some, there was a question yesterday in the Q&A session about how we solve the Kondo lattice problem in the case when there are quasi-particles. We do the static calculations of the saddle point equations. Here you have to do dynamical version of that. And so here, what's shown here are two peaks, two sets of peaks represented by two different colors. Each peak is characterizing some broadly distributing spectral function. And you can trace out these two peaks to see that it's almost like two separate bands. And there's a particular K point, this red line marks, this is like an RPS type of plot, the spectral function energy distribution curve for different values of K. And you can see that there's a particular K where the curves, the two spectral peaks are sitting on top of each other. And that's not a coincidence. That's dictated by the fact that at that particular K, the eigenvectors of the Green's function form a two-dimensional irreducible representation. So if it were block electrons, it means that you have two degenerate block states. That would be a node. Here, it's not a node, but for each omega, the eigenvalues have to be identical to each other, and the eigenvalues is the spectral function. So basically, instead of having two branches of very sharp quasi-particle peaks which merge at this symmetry-dictated K point, now I have two sets of very broad spectral peaks which are merging at this symmetry-dictated point. And so this, you can visually see it, that the peak, the width of the peak is larger than the energy of the peak position measured with respect to the Fermi energy. And this is in sharp contrast to the case when they are sharply defined quasi-particles. So this already visually tells us that it's not a Fermi liquid. And for the two-channel Kondo problem, there's some asymptotically exact low-energy forms of self-energy that was known, and our calculational method captures that. We also find out that in the lattice model, there's this unusual and never suspected hole in the self-energy, and that was actually very important to produce these Kondo-like features, which is dispersing with a very large width. But as a characterization of non-Fermi liquid state, quasi-particles being lost, that's this particular form of self-energy. The fact that it's not linear for the real part and not omega square for the imaginary part. Instead, both of them are both the real and imaginary part of self-energy being squared with omega characterizes the non-Fermi liquid state. We can say more about that. So that already says quasi-particles are lost. And so there was a question about what exactly replaces the quasi-particles. In this case, we can do calculations about in terms of other correlators, such as the spin-spin correlation function, channel-channel correlation function, combined spin-channel sector quantum variable that characterize both sectors together. All these correlation functions for the two-channel Kondo problem per se, it was known that the system fractionalized into Majorana fermions as elementary excitations. If it were three-channel Kondo problem, it would have been some parallel fermions that represent the elementary excitations. So we cannot probe these fractionalized excitations directly. That's one of the outstanding challenges of the correlated electron field. But we can measure the physical object correlation functions. And so the square root omega of self-energy, which is like a T matrix that the conduction electron experiences, captures this consequence of Majorana fermions that's consistent with that. Local charge and local spin and the channel and other correlators should have a logarithmic dependence on temperature, and that we found in our numerical solution. So all these, all our results, all our correlators are consistent with the fractionalization of quasi-particle is lost. Landau quasi-particle is lost, but there are these Majorana fermions which act as the elementary excitations. This being a setting where we are looking for topology, so how do we do that? We can calculate what happens when there's a surface. And so the Fermi arcs was very well explained by both Antoine and Suyan yesterday and today. And so we see Fermi arcs, except that it's extremely broad. And if we look at the self-energy, again, we see this square root omega dependence. And again, we can sit right on the surface and calculate local correlation functions like spin-spin correlation functions, channel-channel correlation functions, etc. Again, these susceptibilities show the same log T dependence as in the bulk. So that provides evidence that even on the surface, we have these Fermi arcs, but these Fermi arcs are not describing dispersing quasi-particles. Instead, they are fractionalized. And we do a few other checks, and anything that we can physically calculate is consistent with the picture that I just described for you. There are other topological consequences, like Hall responses. We can calculate spin, valley, and also the nonlinear Hall that Suyan talked about in the morning. And they all exist. So something like Barry curvature induced effects are still operating, except that I don't have block functions, and I cannot really specify the Barry curvature. So let's just use physical measurable quantities to do the test. And we can see that while the existence of these is consistent with the usual Barry curvature induced effects, the temperature dependence is highly unusual. So the temperature dependence here captures non-Fermi liquid. So in a way, these quantities would not have been non-zero if there were no topology associated with it. But here, there's a very good combination marriage of non-Fermi liquid aspect and topological aspects. And so we are continuing to pursue this direction. It turns out that once you define, it doesn't really take a genius to go from these eigenvectors of Green's function to the corresponding Barry curvature that you can define. And when we've defined that, and we've shown that these Barry curvature are actually useful because it gives the quantization. It's a properly defined Barry curvature. The Barry flux is quantized with respect to this crossing points, and not only that, even in the cases where there are no spectral weight at all, such as some Mott insulators which are built up out of the underlying non-interacting systems that has symmetry protected nodes, it turns out that in this gigantic Mott gap, there are actually some hidden features in the form of zeros of Green's function, which for the many-body-minded people, that's actually nothing. That's the self-energy is singular at that point. And turns out that you can also define crossings associated with the Green's function zeros. And when there's a crossing, this flux of the Barry curvature defined in terms of Green's function eigenvectors, they're still quantized. So well, I have a Mott insulator, so Hall is probably not the best response, for example. We believe, we don't have a proof, that something like quantum oscillation can still be picked up.
What about optical?
Yeah, it's a good thought. We haven't really, it would be very interesting.
And in this mechanical phase, is the temperature dependence outstanding? Like,
we had a prediction, it has not been looked at.
Apart from temperature dependence, is there any other like strong experimental signature one can say that this is not?
Yeah, so right now, we are satisfied because the challenge is that in a strong interacting setting, what do you mean by topology, right? So we are satisfied that there's a characterization, these different surface states, etc. They all exist. Temperature dependence is the most natural quantity because if I started by describing resistivity versus temperature having linear as opposed to be T square. But my sense, and I think that's probably the spirit of your question, is that there should be some other manifestations. And so we think, so for instance, specific on the Green's function zeros, it's not an accident that Green's function, this self-energy diverges. It means that there's some collective sector that has something that acts like a zero mode. And so there should be some sophisticated, maybe some form of high-order correlation functions. Correlation functions of objects which are not the usual spin charge, but some composite objects that should have picked up. But this is the obvious, maybe we should just talk, because I want to pick your brain on such things. Good. So this is before I leave this subject, it turns out that the two-channel Kondo effect is not there just because I wanted a model. There's an element of that. But also, that's constrained by symmetry. I alluded to yesterday that you have 14 F levels coming back to the F electron, to the rare earth and actinide-based intermetallics. You have 14 levels, and it's a crystal environment, which breaks down into multiplets. In a typical case, we consider Kondo lattice because the lowest level is a Cramer's doublet. And then the other 12, you don't worry about it. It's a high energy excitation. But you can actually realize, and this is not our original contribution, this is the contribution that the heavy fermion community has been making over some time already, that, for example, you can think of this local moment as not spins, but orbitals, degenerate orbitals. And then the degeneracy that protects, the physics that protects the degeneracy of these two channels of conduction electrons is actually Cramer's degeneracy. And so one would like to realize a non-Cramer's doublet of these 14 F orbitals as lowest state, and then leaving the spin index for protecting degeneracy. And so using that, and it turns out that cubic lattice is what's needed, you can use that as guidance to do database assisted search. We only looked at some particular space groups, looked at uranium and praseodymium. We found these three, in which the crystalline symmetry constraint on the local degrees freedom cooperates with the symmetry constraints on the degeneracy, or in our language, crossings of the spectral functions. And so these are the candidates, and our collaborator, the Vienna group of Silke Passion, has made this material, provides some evidence for two-channel Kondo nature of the material. So these are very much ongoing things. I want to mention one more case where instead of dealing with like two-channel Kondo lattice, which gives us quantum critical phase, we can also go to the quantum critical point, very much like what I ran through in the first part of this talk, that let's go to the quantum critical point, anti-ferromagnetic quantum critical point of this lattice model that has interesting symmetry constraints. And so quantum criticality is signified by this omega over t scaling and also fractional exponent. And then you can look at a single particle spectral function to see that, again, it's very broad and it's not Fermi liquid. Here we don't have a characterization of fractionalization. We just don't know. We know the quasi-particles are lost. But something very similar happens, that there's a symmetry-protected degeneracy associated with this peak. So we have these Weyl nodal states, which goes beyond the quasi-particle description. And in fact, there's an experiment in Vienna in this compound, which already had the almost like self-organized criticality in this quantum criticality in this material, and they have evidence for topology that's developing out of such a non-Fermi liquid state. So in terms of coming back to the theme, I started this part where we have non-Fermi liquid topology. So we're using strange metallic state breakdown of Fermi liquid description as the vehicle to realize topological states, gapless topological states that are not adiabatically connected to the non-interacting case. But the flip side is that, in fact, that was very much part of our motivation getting into this topic, that topology is enriching correlation physics. So do I have a few minutes, or am I done? Okay, good. So as I said, I promise I'm not going to get into the details of the flat bands, but at least I want to give a hint that this is a new setting that could explore both the topological aspects and the non-Fermi liquid aspects. And maybe there's, again, interplay between the two. So flat band systems, it was beautifully introduced by Ming yesterday. I'm using the same example of Kagami metal. Without spin orbit coupling, with near stable coupling, you have exactly flat band. And this is the picture of destructive interference that's responsible for creating two Y bands, and then this one where the electron is going nowhere because of destructive interference. And so the immediate motivation actually came from precisely what was talked about by Ming yesterday. There's quite a few examples of particle and Kagami lattices in which non-Fermi liquid behavior has recently been reported experimentally. So we want to think about this. So it seems to be natural that the flat band should act as the analog of the atomic F orbitals. And so therefore, I could take this flat band as the F electron analog and these Y bands as the SPD electron analog. So I should be able to write down a Kondo lattice Hamiltonian immediately. It turns out there's no free lunch like that. If you think about this destructive interference, just wipe out the sites that have zeros. Let's not worry about them. So then you get this object. You see the sign change 3 times as you go around. So that's LZ equals 3 state. This is called a compact localized state, except that this compact localized state is not a good basis because if you think about this compact localized state and the one sitting nearby, clearly they're not orthogonal to each other, right? So that's not a good basis. And it's not even complete. So recently, we were able to combine, it was the clever trick from Lei and Lei Chen was the audience, and Hao Yu Hu, that they identified they avoid this no-go theorem of construction of proper Wannian states. It turns out there's some combination of this flat band and wide bands in which one can properly Wannianize it. And you can see that this is the most compact Wannian orbital. It's almost like this, except that you have tails that's decorating. These tails are very important to make these what do we call compact molecular orbitals to be orthogonal to each other, coming from neighboring unit cells. And using this, it turns out that this is a slow lane and fast lane, this local moment species and the conduction electron species actually come out. And so again, we reach this slow lane in combination with fast lane, some ratio of the velocities that gives a small parameter that would allow theoretical progress, except there's a twist. These are all topological bands. So here we go. There's the opportunity for discussing strange metallicity, as Ming already talked about yesterday. And there's an opportunity to use this kind of basis to do the Weyl Kondo semimetal, both in the settings with fermi liquid, but small quasi-particle weight, and perhaps also destroying the quasi-particles completely. So I want to showing again the long list of collaborators, which I described yesterday. And I particularly want to recognize contribution of our collaborating group, Silke Fasching from Vienna, where there's a lot of two-way street in the motivations, thinking about such problems, and so on. So this is the summary. Thank you very much. Please. Yeah, so I'm not going to flash it back. So you have, remember the experimental plot where you have low temperature, you have the blue regions of fermi liquid, T square resistivity, and this tornado which comes out, which is anchored by a point in the zero temperature limit. So this orange region, this tornado region is where strange metallicity and loss of quasi-particles. It's not. Maybe let me show you that. I can show you a theoretical phase diagram, but I think that experimental plot is probably more striking. Sorry about this exercise. So, I think Mike Manfrey would appreciate such things. The cutoff is 0.3 Kelvin. So it's not all that high temperature. And temperature is high by certain measure. If you ask what's the amount of entropy that's living in this orange part of strange metal, reaching T linear resistivity and other things happening, it's almost like 50% of the unitarity limit, which is R log 2. So like almost half of the spins are part of this quantum critical fluid. So in that sense, it's actually extending to extremely high. You would think that a point in the zero temperature limit shouldn't have a very large region of inference, right? But in fact, it's reaching up in temperature over a very large region of the energetics. And this, to us, is actually important because just as a hint of at least the kind of things we're thinking about, if you want a high temperature superconductivity to be driven out of such a quantum critical normal state, you want something that's very robust. And so the fact that quantum criticality is involving such a large set of the degrees of freedom should play an important role for getting high TC, for example, by a certain measure. And these are the kind of things we are pursuing theoretically. Yeah, please.
Is there a simple picture of what disrupts this Kondo semimetals?
Yeah. So I think I may have a picture. It's a very good question and a very important question in many ways, and it's also a conceptual question. So maybe I can use this as illustration. So please ignore all the details. I just want you to focus on this renormalization group flow. So if I only have a Kondo coupling, it's an anti-ferromagnetic coupling between two spin species. So clearly, energetically, it pays to form this Kondo singlet, right? And that Kondo singlet formation in the ground state is the basis of the heavy quasi-particles and the ferroliquids. So there's a fixed point which describes that. So you can ask the question, what is it that wants to destroy it? Because Kondo scale is our ultraviolet energy scale, so something has to be equally powerful. And so in this case, it turns out there's a competing fixed point. That fixed point is because the RKKY interactions between the spins really want to gain energy by forming singlets among themselves. So I have a species of local moments, and I have conduction electrons. The Kondo singlet is across the two species, but the RKKY interaction wants to form singlet among the spins within this species, among local moments. Across different lattice sites. And once they form singlet, they could either condense into an anti-ferromagnet or form spin liquid and other things. Quantum magnetism has a life of its own, right? So it's really the quantum magnetism which has its own energetics that is strong enough to compete with the energetics of locking the two species together. And so that's why in practice, what you do is to tune the ratio between the RKKY and the Kondo interaction. So that kind of qualitative picture was actually already recognized some time ago by Doniak. But to realize that this competition happens dynamically is in fact part of this ingredient, realizing the strange metal behavior.
All right. We're running out of time, so let's thank you again.
Thank you.